We can start. Good afternoon, guys. So today we will continue talking about chat models. So last time we stopped on this Instruct GPT paper that described three stages how they trained actually chat GPT 3.5. Uh, so the first stage was to collect data, um, like dialogue data, questions and answers, and fine-tune large language model on this data. So let's look at this stage. First of all, um, First of all, why can't we use the normal language model as a chat model? Because it's trained on general data, and it so a lot of books, textbooks, and it just returns that it has seen during training. So it kind of continues your phrase as it would be in textbook. Um, so this is why we should um, fine-tune our model to force it to continue the phrase not as the um, um, some textbook text, but as assistant. So that's why we need to use a data set, conversational data set, where one person plays a role of the user, and the other person plays the role of computer. And the second person, assistant, should continue the conversation. So this is the first stage, to create data set for dialogues and fine-tune the uh, language model on this data. And there are two ways to do this. One way is to fine-tune the entire model. The other way to use low-rank adapters. So let's, yeah, these are different domains on which they trained the model. I don't see here the code data, like um, writing or checking the code on the correctness, but of course they also used this data set. Um, so uh, yeah, let's think about how much computational resources it will need to fine-tune the entire model or with low-rank adapters. So for example, if our model has let's say 100 billion parameters, and every parameter uses 16-bit precision, and typically they use 32, but 16. Then it will be 200 gigabytes, one because one 16 bits is 2 bytes. So we will need a GPU with 200 gigabyte memory just to store the model. But we need also gradients. So it will be 400 gigabytes. And in Adam, we also need the momentum, the parameters of mean and uh, standard deviation. So it's plus 400. So it's about 800. But large models, they have more than 1 billion parameters. They have one 20, 160 billion parameters. So it's more than 1,000 gigabyte memory. So it's you can understand that it's hard to fine-tune the entire model. Of course, large companies like OpenAI, they were bought by Microsoft, so maybe they got money for GPUs to train the entire model after that. But in practice, we should use low rank adapters because, for example, a low rank adapter will use 20 gigabyte of memory, and then it will be about 100 gigabyte for training. So this is the observation from Yandex company. They also work on voice assistants, on chat models. So they noticed that because we don't have information from OpenAI about training, but this is also the it's also earlier stage of their large language model production. What is doing now there, they also don't report. So it was noticed that when our model is overfitted with low rank adaptive training, the result, which was measured, I don't know how it was measured, maybe just people used the preferences and ranked the answers. But so the result of the chat model was still improving. You remember from machine learning class, we should stop when validation loss goes up. So in this case, we if we continue training the resulted model is improving. So it's an interesting observation. So the other reason why should we use fine-tuning? Because the model could see the data. So, for example, he could see information about who killed Pushkin. Pushkin is like Shakespeare in Great Britain, very famous poet in Russia. The model could see this information, but when it generates the answer, it could forget this information. So so that's why because it just generates tokens and the model could see some texts. I don't know, like quizzes, who killed Pushkin, and had different choices, and provide just another name. So this is another reason why we want to fine-tune the model to make it more factual oriented. So, for example, if you want to train chat assistant for one company, of course, you should train on the data from this company. But still, it's too general data. And to make this more specific, in Instruct GPT, they proposed to use so-called guided preference fine-tuning, and which is called reinforcement learning with human feedback. So the second stage was to train a reward model. So what this model does, it reads the output from language model and returns one number. This number we can interpret as ranking. Why we can't use just so they hired 40 people to rank the outputs from language model. So, for example, there was a prompt, like a question, and large language model generated the answer. And if we use different sampling methods from grid search, it would return different answers. So these different answers were given to these assessors, and they ranked these replies based, of course, on instructions provided by OpenAI. For example, if there was hateful speech, they had to rank lower this answer, and so on. This is example from Yandex company, how this ranking system looked again on the early stage for these assessors. Typically, it's multi-choice or binary. This is example for uni variant model, where they just ranked one reply. And yeah, so why we can't use the human feedback, the people's ranking? Why should we train another model? Why do we need to train the reward model instead of hiring maybe thousands of people, and every time we want to compute the gradient of our model, we ask people to rank the answers and then aggregate these rankings and use in our loss function and calculate gradients. So why it's better to use a model that will provide ranking instead of on every iteration use people to get rankings. Why do you think we need to train another model to substitute people?
The model's a lot cheaper and faster.
Faster, cheaper, maybe. you can find people who will. Well, actually, there was a long HR process to select these people, because these people actually influenced the large language model infrastructure more than all the other people in the world, because actually their rankings were used to train the reward model. So yeah, I don't think they were paid the low salary. So yes, to make it easier for automatic computation, but also the number of outputs from large language model is huge, and you can't label all possible answers from the model. So this is another reason. So how this model is trained? You can take a BERT model and create a data set with, as I mentioned before, so here is an example, with input prompt and different variants of the answer from language model. And then ask people to rank these replies. And unfortunately, we don't have the absolute scale for ranking, because BERT model just returns probability or logit, a number, and if it's 100 or if it's 1, we can't actually compare these numbers. So they used the relative scale. For example, one sentence was a winner, like had high ranking, and another continuation sentence was a loser, the lower ranking, and the BERT model returns some number, classification number. We call this reward for one and for the other sentence. And then we will take the difference between these outputs from the BERT model, apply sigmoid. You remember sigmoid converts into range between 0, 1, and log. So, for example, if the low rank sentence BERT gave the same rewards as to the higher ranking sentence, then this difference will be close to 0. And do you remember what is the value of sigmoid of 0? No, 0.5, because it crosses the origin. Yes, it will be 0.5, and log of 0.5 won't be small number. It will be negative, so we use negative. And it will force the model to change the weights of our reward model to reduce the loss. If our if our model returns higher ranking for the winner and lower ranking for the loser, then this difference will be large, a large positive number, and negative log will result in small loss. So we don't need to actually make this loss smaller. And another interesting observation, if you remember this, how the sigmoid function looks like, for large numbers, the gradient will be large, small,
small.
Yeah, it will be a kind of zero. So if our model, the BERT model, learns to classify the winner higher than loser, then it won't update weights because the gradient will be close to zero. Well, so this is the loss function which is used to train this reward model on pairs of the data. And if you look at the prototype of homework that I'm using for homework on the link, you can see there's also a library from Hugging Face that will train the reward model on the data set. And the data set can look like there was a data set from Open Assistant. This was a project to create a chatbot, but it ended up in creating a nice data set. So, for example, they have different messages. Messages have parent ID, user ID. So user ID is the answer continuation of the dialogue with parent ID. And so here's an example. Can you write a short introduction about the relevance? And there are some metrics like toxicity, severe toxicity, mild toxicity, and so on. So sexual explicit. So for example, yeah, you can use these numbers as rankings for for example for two so user oh, sorry, message ID. I said user ID for two use message ID with the same parent ID. In the simplest way case, you can just, for example, if you want to uh, fine-tune on sentiment analysis, you can just use the BERT, which was fine-tuned on sentiment analysis, and use this one negative one labels as the reward. So this is the simplest way. But okay, let's go back and understand why actually our original model will update the weights in the way that the user will like more the outputs from this model. Mm. And this is the third step. And the third step is actually the of updating our original model with information from the reward model. And let's look how it works. But before we will talk about this fine-tuning with human feedback, it's important to understand that even after the first stage, your model will work pretty well. Typically, this second stage adds just fractions of percent of improvement to your model. Um, okay, so Now let's talk about why it's called reinforcement learning with human feedback. First of all, it just uses one technique that was used in reinforcement learning. There is nothing else from reinforcement learning. So if you're not familiar with reinforcement learning, it's completely fine. So let's denote our original model. I will call this assistant model as pi of a given s, where, as you remember, large language model returns probabilities of next token. So s will be the prompt or previous dialogue. And a will be generated answer by our model. So that's why we use this notation, a given s. S is given, and a the output from our model is generated text. How to calculate this probability? Do you remember how we can calculate this probability from our transformer model? We have logits for every token. We have logits, but in our A, we have actually multiple words. So A, it's maybe 2048 tokens, A1, A2, and so on. So to calculate the probability, for example, we can take the probability for token A1. You remember we have in the last output layer the logits of the size of the dictionary, and because we know the word A1, we will take the logit with index for this word A1. So we will use this, well, we apply softmax, and this will give us the probability of token A1. Then we'll look at the logits for the second token. Again, we find the index of this token, and we will get probability of this token. And then we take the product of these probabilities. So this is how we can calculate the probability of the entire phrase. And of course, we should use log probabilities because you remember the product of numbers smaller than 1 will result very rapidly in 0. So instead of product of probabilities, we typically use the log of product. So, okay, I hope now you have idea how to calculate the probability of the phrase that our model produces for a given prompt. On the other hand, we have reward model. Reward model. Reward model, okay, and also let's use some parameters. Let's denote the weights of neural network for our language model by theta, and the weights for neural network for a reward model by phi, for example. Um, so a reward model has two inputs, and input prompt and a continuation. So that's why we use two arguments as inputs to the reward model. And what will be our target function? What we want to maximize? What do we want to maximize? We want to maximize expectation of reward, actually, expected value of reward. So how to calculate this expected value? So it will be, if we think about the joint probability on A and S, the joint probability will be a product. So probability of on both A and S will be the product of the conditional probability times probability of S. And the conditional probability actually we have from our language model, phi. So, I mean, formally, I should write here double integral over S and over A with a probability over A and S times reward. That depends on A and S. But because these joint probability can be represented as the product, we can represent this double integral as iterated integral. One integral will go over all possible prompts. And the second integral will go all possible continuations of our model. Okay, so now which parameters we want to change? Do you remember? Do we want to change phi or theta? What do we want to fine tune? Reward model or assistant model? Assistant. So we should maximize this because it's reward. We want to maximize this with respect to theta. Yep. That's you. Okay, so the next question is how to calculate this integral. Over all possible prompts and over all possible continuations. I think David knows the method. Monte Carlo, yes, estimation. Who Who doesn't know what is that Monte Carlo estimation? Oh, okay. So, this is the standard method which is used in machine learning when we want to, or in mathematics when we want to calculate integral. Or for example, for normal distribution, there is no closed form integral. So, okay, Monte Carlo is it was proposed for by physicists during this nuclear project um, to calculate the multidimensional integrals, and because it's a statistical approach, they call this Monte Carlo because there is a famous casino in Monte Carlo. So the idea is to estimate the integral, for example, of a function f of x by the sum um, by the sum at some points x. Oh, yep, at some points x. X. Wait a second. F of xi, where points xi are sampled uniformly from interval, let's say from a to b, or maybe from x0 to x1, for example, because I used a, where x is sampled uniformly from uniform distribution on this interval. So why actually so instead of integral, we will just sample points, and you can use any random number generator, calculate your function at these points and sum up. And the results we will get, it will converge with large number of points to the integral. This is the result is known as the law of large numbers, because the law of large numbers says that the sum of random variables. Okay, it's a little bit out of topic, but this is this method which is always used in loss function estimations. It says that if we have the sum of random variables, do you remember the law of large numbers? Where should converge this sum? It should converge to the mean, to the expected value of f. And what is the mean? The mean depends on distribution. The mean is the integral, so that's why we will get integral estimation of the probability density function p of x times our function dx. So if you use the uniform distribution probability, what is the PDF for uniform distribution? It's 1. Okay, so we use p as 1 here, and the expected value with p equals 1. Well, in general, you can calculate any arbitrary integral But in this case, you will need to sample x not from uniform distribution, but from distribution P. Okay, so this is the idea how to estimate the integral with the sum. Okay. The first step, we will approximate the integral over all prompts over S. And I will take the sum of one point. Typically, I mean, in practice, we take the batch, and then it will be this. We will take the number of prompts the same as the size of the batch. But I can take a batch of size 1, and the first integral will just disappear. So this is the first Monte Carlo estimation. I just used n equals 1 in Monte Carlo estimation. Does make sense? Okay. So the second step, we can try to estimate the second integral as well. Oh, but in this case, I should use a specific prompt. Let's call it S prime. So I just sampled one prompt. Then we can try to apply the Monte Carlo estimation for the second integral, and then we will get, for example, if we take n continuations of this prompt, it will be sum for I from n, reward model, calculated at some continuations AI for prompt S prime, where AI are sampled from our language model from pi. Okay, so now we don't have integrals. We have finite sum. We just need to sample n, generate and run our language model n times. But can we calculate? So the next step, we want, if we denote this function as j of theta, we want to maximize this function. And the most popular algorithm is a gradient descent. In this case, it's gradient ascent. So we update our weights of our original assistant model by this formula. Oh, plus, I'm writing this simple version of gradient ascent. Of course, in practice, we use Adam with a little bit more complicated estimation for learning rate eta. So this is our goal, to update the weights of model with information from human preferences. But if we use this approximation of the integral, can we take a derivative with respect to theta in this sum? There is no theta. So this means that the second approximation is not useful for our case. Let's try to calculate gradient first. So I will use my first approximation. Oh, instead of equal, approximately. And so what should I do next? Do you remember which trick we should use to estimate the integral of the gradient? Log derivative trick. So, and then we will use so-called log derivative trick. I think we will just write this down and stop for today. If you calculate the gradient, do you remember the gradient of the log? The gradient of the log of pi will be 1 over pi times the gradient of pi. So we will substitute the gradient of pi as pi times the gradient of the log. So we will use log derivative trick. And rewrite this as pi times gradient of the log of pi. And now we have the probability here times some function. Probability times some function is expected value. And the expected value we can again approximate with Monte Carlo. In the previous integral, we didn't have probability times something, so it wasn't the expectation. The second integral is the expectation. So this is the now we will use Monte Carlo estimation. Now it will actually provide the result. So we will use 1 over n sum and under the sum we will have log times reward. Log times reward. But we sample the outputs from our model here. Where these continuations are sampled from our model. So now we have theta in our loss function. Okay, and this will be our second table. Write down theta of a given X prime. And this will be our algorithm to update the weights of our model. And it's called PPO. We will talk in reinforcement learning. S is called states, R is called action, and pi is called policy. And this algorithm is called policy um, uh, based algorithm. So yeah, let's continue next time. So it's called PO, policy optimization, but the method which is used PPO, projected policy optimization. And this algorithm also is implemented in Hugging Face. And when you will do the homework, it will run this algorithm for fine-tuning with the reward model, your model. Okay, let's stop here. Yeah, and sorry, just one more information. This algorithm in reinforcement learning is called reinforce. And this is the only connection with reinforcement learning, the name of algorithm which is used here. Mhm.